Okay. Hi everyone. Good evening. Thanks for coming. I hope this meetup will give you a sense of what natural language processes and some of the techniques that they can be translated into a business value. So let's go through the agenda. I'm going to speak 30 seconds about me, and then we're going to go through the concept of natural language processing. We're going to see some vectorization techniques and the difference with word embeddings. Then we're going to switch from word embeddings to sentence embeddings. Then we're going to see a demo, which is going to wrap up whatever I said theoretically in a piece of code in Python. And then I'm going to share in the end my lessons learned from experience in working in this field. Okay, so I'm a computer engineer. A little bit about myself. I studied at Politecnico di Milano, but I also got a master from the UIC, University of Illinois at Chicago. And I actually studied with the founders of Bildo, which is hosting us tonight. So thank you for that. I had some experience in the data science consultancy field in the US. And I also worked in the e-commerce space for a big company, American company called Grainger. And then I moved back to my native country in September. So I now work for an energy efficiency company called USAID. And if you have any questions, any doubts, or just shoot me an email. That's my email address. I think we're going to share this deck right after the talk, so feel free to contact me. So let's get through the core of this meeting. And to get things started, I would like you to take 15 seconds, not more than that, to read this slide. Okay. I hope everyone had a chance to read the whole thing. What I'm trying to say here is that right now, your brain, trying to understand the concept behind this text, just perform what the goal of NLP is. So it's trying to understand and comprehend some text that we just proposed. We did it with the human brain. Now, NLP, what it does is it tries to translate the same concept to the machines. So we're trying to give the machines the power to comprehend the text and the language that we write. Somebody can say, okay, this is kind of futuristic in a sense that this is too much future for me. Always techniques are not that far. And that's why I'd like to show you 15 seconds of a video that came out a month ago, so probably maybe you saw it, maybe you didn't see it. I think it's worth watching it. We're gonna see, hopefully the audio is gonna help me with this. This is a call, we're gonna hear a call between an AI agent and an actual person. So.
Sure, what time are you looking for around? At 12 p.m. We do not have a 12 p.m. available. The closest we have to that is a 1:15. Do you have anything between 10 a.m. and 12 p.m.? Depending on what service she would like, what service is she looking for? Just a woman's haircut for now. Okay, we have it 10 o'clock. 10 a.m. is fine. Okay, what's her first name? The first name is Lisa. Okay, perfect. So I will see Lisa at 10 o'clock on May 3rd. Okay, great. Thanks. Great. Have a great day. Bye.
I think this is kind of amazing. This was presented at the Google I/O a month ago. And what we're seeing right now is a machine that is actually doing an NLP task extended and trying to perform a lot of actions, and is acting like a human. And the great thing is that on the other side, there is somebody who doesn't know that, and truly believes he's talking to a human. So that's what NLP, the state of art in NLP today, is we're here. And which means that what I was trying to say earlier, that we're trying to let the machines do whatever we're doing with our brain, reading and text, it's actually achieved. Now it's all about optimizing it and making it in a way that business can get value out of it and everyone can get support out of it. So it's a pretty mature field. And of course, there's not only that application that we saw, there's a list of applications, and I think there's a lot of commercial products around the web. There are kind of examples of what NLP can achieve, and I can go through the list, and it's, for example, machine translation. We all know Google Translate. We all know, maybe we all don't know the Reddit. Reddit is a collector of news. It's an American website, web app, and what it does is essentially reads whole articles of data, of text, and generates automatically some headlines, which is pretty amazing. It's like the natural language generation, which is one of the tasks that NLP does. Sentiment analysis. I think everybody heard about Cambridge Analytica. Sentiment analysis has been there for some time now, and it's giving really good results, and that's why a lot of companies are going towards NLP to add value to their company. And then we have things like lexical semantics. There's a Thesaurus, which is a website that gives you synonyms, and Siri's listening to us. Web application search like Amazon. So this is an important concept in the sense that every e-commerce, everything that involves a search can be, we can add value to those guys if we add some NLP tasks. And what I mean by that is, if you think about search, let's think about Amazon. We're always looking into searching whatever we write in a catalog that can be millions of products. Amazon, I'm pretty sure that it has millions and millions of products. So when we do that search, what we try to achieve is that we try to get results very soon, very quick, and accurate. What NLP can do is, if we try to narrow that search down to the category we're looking for example, then we're helping search. So we're helping all these companies, all these e-commerces, and in general, all the companies that are based on search to do better search. So that's really important. And then chatbots, it's a trend. So we heard some kind of chatbot in the video, but behind a chatbot, there's an NLP task which has been performed, and many others. So let's go to the crux of this meeting, in the sense, okay, we talked about generic things, we saw video, we talked about chatbots and all of that, but we have to start somewhere, right? And the start is, how do we enable those machines to actually read the word data? We have to find a way to pass word data to our algorithms. And what we do is actually transforming the text into some kind of numerical features, because we all know that machine learning happens on numerical features. And there are different ways we can do that. So there are different ways we can enable NLP. We have to transform a word into a vector, and there are this is just a list of things we're going to talk about tonight, but there's more techniques, and as I speak, I think there's somebody publishing a paper on how to do that task faster. We're going to start with probably the most intuitive one, which is called the bag of words. And it's very intuitive, and to actually understand the concept behind the bag of words, I'm just going to write an example, for example, two sentences, sentence 1 and sentence 2. And we have sentence 1 that says, without music, life would be a mistake. It's one of my favorite quotes from Nietzsche. And the second one that says, Radiohead are a great music band. Okay, so we have to find a way to make those two sentences, we have to feed them into a machine. So what can we do? All right, one idea is to say, okay, we take a dictionary of all the words that I used in my corpus, which in this case is just these two sentences, because it's an easy example. And we just label the word 1 if we use that word, the specific word, or 0. For example, without music, life would be a mistake. So we have a 1 for sentence 1 that says without, it's in that sentence. Music, it's in that sentence. So it's going to be 1, 1, 1, and so on. And we have our first sentence transformed into a binary vector. And then the second, the same thing we can do with the second sentence. So we don't have the word without, so we're going to have a 0 here. But we have the word music. And actually, music is one of those one of the words that we have in both sentences. And here we are. I mean, we passed from a word representation of our vocabulary to a vector. And now we're ready to run machine learning on it. Pretty cool and pretty intuitive. Now, the problem is it's fast, okay, it's easy to implement, but we talked about 2 sentences, and we kind of understood the fact that these metrics will grow as we grow the number of words we use in our corpus. And there's no company that actually uses, that does really text mining, that uses like small dictionaries. We're always talking about billions and billions of words. Let's think of Wikipedia dump, Google News. Those are the famous data sets for NLP. They're pretty big, and so these metrics will be pretty huge, and it's going to be heavy computational to do all of this. So we have a problem of dictionary size, and we also have another problem that some algorithms don't like, which is the sparsity of the data. In the sense, sparse is a vector that contains a lot of zeros. So it's kind of a waste of information, the fact that we have so many zeros. So that's another con of bag of words. And then we don't care about, I mean, bag of words doesn't care about the word order. So if I said without and I put it at the end of the sentence, it will be the same for bag of words. So great. Well, we have another technique, which is it's called a hashing trick. And whoever is a software developer knows what is a hashing function. And who doesn't know what's a hashing function? We simplify by saying that given an input, which in our case, we're talking about words, it gives us an output. And it gives us an output which is John Smith is going to be number 2, for example, and Lisa Smith is going to be mapped to the vector 0, 1. Now, we have to discuss this because it's easy to understand. It's not as easy to find a hash function which satisfies our dictionary because we have some problem. The same input and the same output, that's great, which means I have the hash function. If I put John Smith right now, it's going to be number 2. But if I put it tomorrow, it's going to be the same. Same input, same output. Great integrity. Now the problem is, the other good thing is that the range is always fixed in the sense we are the ones that say that we want to map our hashing function to this type of domain. In this case, it's number from 0 to 15, but we can choose to have vectors which range from 15 to n. So it's our choice, which is a good thing to have. But hash is one way. And what it means is that if we have number 2, we're not sure, we cannot go back to John Smith. And in this case, that's one example, but so we can go back. And sometimes this is not a problem, but sometimes it is. We want to be able to track what we do. So we want to be able to come back to whatever we started with. And the other problem is that collisions. So hashing functions has a problem. Collisions happen. Collisions happen because we're trying to map one space to another space. And the other space has to have the right number of dimensions to cover all our possible inputs. And that's kind of, it's always a trade-off between what we have, what memory we have, and what hashing function we're choosing. So it can be a problem. So that's hashing trick. There's another thing called the Tf-Idf, which is somehow very close to bag of words. And that's why I'm pulling back my example from earlier. But the concept behind Tf-Idf, which stands for Term Frequency Inverse Document Frequency, is that let's take, for example, a book. A book is it's full of words, and there are some words that are repeated more than others. Let's think of, for example, the article, the will be in a book thousands of times. Instead, if we have some rare words that at the same time contain a lot of meaning for us, in bag of words, they have the same weight. Now, Tf-Idf, what it does is trying to weight those words in a way that common words don't matter that much, but rare words do matter, and that's what we're trying to do with Tf-Idf. That's a mathematical form, but that's telling us that the number of documents the number of documents that word is in, it's going to give us the weight of the specific word. And these two vectors, if we look at it from the previous example, what I'd like you to notice is that music, which was the one that had 2 ones in it, now it has 2 zeros, because that word, it's repeated twice. And our corpus is 2 sentences, so probably that's a high number, and we don't care about that word. It means it's very repetitive, and probably it's it doesn't have any semantics. So it has a 0 weight. Now, the things are pretty much the same as bag of words. The only thing that changes now is that we know how much a word weighs, which is something that it's good to have when we do machine learning. So that's great. But so far, we've been talking about vectorization techniques. And vectorization techniques, they're just trying to put words into vectors. We're doing some counts, we're doing some stuff, but the goal of it is just transform into vectors. So, and bag of words is a simple example. Now, word embeddings came with the idea of putting semantics into our vectors. So we want the words to be vectors, and we want them to have a semantic. We want them to have a meaning. And in 2013, if I'm not wrong, Mikolov, which is a guy, published a paper called Word2Vec, which suddenly became a standard for the NLP. It was a great work because it was the first one that, one of the first one to make such to achieve such a goal in a probably easy way, in the sense that at the end of the day, Word2Vec is a neural net, neural network, and it's a shallow, so it's not a deep net. And it's really simple what it does. Now, to understand what it does, we're gonna try to, I'm gonna pull back my sentence from the earlier example, which says, without music, life would be a mistake. Okay, so what's the goal of Word2Vec? The goal of Word2Vec is to say, okay, I'll fix a context window, which is telling me, okay, I'm not gonna take the whole book all at once. I'm gonna try to fix my window to, let's say, 6 words or 7. I'm gonna pick one word at a time and try to see the probability of seeing one word given the others. And I'm gonna do that for all the words in my context window. So, for example, if I start with life, I'm picking life and trying to understand the probability of seeing life given without, and do probability of life and given the word music, and so on. And I'm gonna do this for all my words in the context window. I'm gonna take that probability, I'm gonna try to maximize that probability. So that's what behind Word2Vec is. And depending on how do we achieve this task, we have 2 architectures, 2 different, slightly different implementation of Word2Vec, which I was trying to say, it's a shallow network. So there's one way, which is called SIBO, or which stands for Continuous Bag of Words, that says this. It says, okay, let's take all the words that you see in blue, and let's try to predict the word life. So we take the context, and we're trying to predict the word. And in the other architecture, called skip-grams, what we do exactly the opposite. The input is going to be the word, life, and the output is going to be the context. So I'm going to do given life, I'm going to try to predict the whole context. And that's pretty much what's behind Word2Vec. And there's a lot of mathematics behind, and I'm not sure we're going to be in time to talk about the mathematics, but if we can, I'll be happy to do it. But what I'm trying to say is that at the core of the algorithm, that's all we have. And doing this, it made Word2Vec one of the most standard in the NLP. Okay, so it became a standard, and it's pretty cool. Mathematics are fairly easy to understand, but what do we gain? What's an example? Okay, let's take an example. Let's think that we take the whole Wikipedia dump I was talking about earlier, and we feed it into Word2Vec. And we do the comparison, the probability of each word for the entire wiki dump, which is pretty big. It's, I think, 1 billion words. Okay, so the output that we expect, it's a vector. So given a word, I will have a vector. And I'll take a word man. The word man, and I'm drawing this into a 2D space. Word2Vec actually works with a lot of dimensions. It's usually 100, but it can get average 300, or it can be as big as you want, because you can also make that the same network. And with some PCA, we bring it back to 2D, so we can understand a little bit of, give it a logical sense watching it. So that's the word that we have for man. That's the vector that we have for man. Now we ask Word2Vec, what's the vector for the word woman? And we get this. Okay, interesting. So the third question we ask is, okay, we want to see where the word king happens to be, and that's where he goes. Okay, cool. But what if we have some mathematical semantic embedded in our vector? Okay, I'll explain it better. What if I take the difference between man and woman? If I take this vector here, and we know that man and woman, the difference between man and woman is the gender. So we make an hypothesis, and we say, what if this vector is the gender vector in the space? And we try to translate it into, to our king vector. And we go and check what's here. And we're gonna see and ask the Word2Vec, what is here? And ta-da, we have the word queen. So Word2Vec semantically understands not only the word, not only maps the words into the space, but it only can do analogies. And that's pretty powerful, because remember we started from the basic concept that it's an unsupervised learning. We didn't say anything to the algorithm other than just take this whole dump of data and feed it into the network. That's what we have, and that's pretty powerful. It can do a lot of more things. That's just the gender vector, but we have different types of vector. We can do things like syntactic vectors, like walking to walked or swimming to swam, and trying to understand the past and the present tense. Or also we can say, okay, Spain is to Madrid as Italy is to Rome. So we understand a lot of different semantics from our training data, and so on. So it can do speech tagging, name, identity recognition, and so on. Pretty powerful. And okay, so Word2Vec. We said that in Word2Vec we try to predict the other word in a way, because we're picking two words and we're saying, okay, what's the probability of seeing the other word? So it's kind of a prediction. At Stanford, there are some smart guys, and that's not news, but what they said was, okay, can we try not to do that thing, which is pretty heavy? It involves something called softmax. It's heavy computationally speaking. And they said, all right, can we go back and use some kind of stuff which is a co-occurrence matrix, which essentially is a matrix where we map every time that we see two words together, we add a count. Okay, so that's what the co-occurrence matrix does. And we're kind of doing the same thing, but we're keeping these co-occurrence metrics to kind of give us a boost in terms of speed of computation. And we kind of doing the same thing. We're doing the co-occurrence matrix, and then we have this huge gigantic matrix, and then we do some SVD, so we're trying to squeeze that matrix in a product of two. And we're still talking about using the cosine similarity. I'm sorry, probably skipped, but Word2Vec, what it does is, okay, I have a vector, I have another vector, I'm trying to maximize the probability of seeing those two vectors. But what it means is that, how do I compare two vectors? The easiest thing to do is to take those two vectors and the cosine similarity between those two vectors and maximize the distance. And that's what Word2Vec does. But GLOB does the same. GLOB stands for Global Vector, and it was made in Stanford. And the essence of this is that we have Word2Vec, we have GLOB. What should I implement if I implement it myself? it would be global vector because it takes a little bit less. And accuracy-wise, all the papers that publish numbers about that tell us that it's kind of the same. So we'll go with glob if I had to choose, but that's probably my opinion. Okay, great. Glob made it better. Great. But we had some other enemies at Facebook. Hopefully nobody works for Facebook, but they're pretty genius. And what they did was kind of making whatever those guys did with Word2Vec and glob kind of look like trash. And what I'm saying this because they kind of they kind of achieved the same results in terms of accuracy, but with some performances which were just amazing. So those are just a screenshot of some comparisons that you usually do when you do papers. And if we look at the time that it took for these famous networks, neural networks, to train on these data sets, we're looking at possibly 2 days versus, this is fastText, 9 seconds. And that's pretty, like, how can you beat that? And it's not only that, it's kind of everything here. And the fastest here looks to be, and Lecan is not really the last guy coming in the AI space, quite the opposite. So, and these all networks which kind of optimize this part became also ridiculous compared to 1 second timing. So, okay, that's kind of unfair in a way, but what I say is that I like to say this in a sense, everybody kind of knows Kaggle or heard of it. It's a competition platform where data scientists do competitions with data. And I read once a quote from somebody that won a competition that said, when you're in doubt, just use XGBoost. So what I like to say is that you do the same if you're doing text mining, and if you want word embeddings, just use fastText. It's going to save you a lot of time. It's just 1 line of code or maybe 2 lines, and you achieve the same results of all the others that I spoke about. Great. Word embeddings are great, but let's go back to the natural language speech. And what I was saying was that we're talking about language. Humans don't speak like with words. I mean, some do, but we need some kind of more than a word to kind of express ourselves, as we saw from the video. So we need something that not only takes a word, but it takes the whole sentence, and it tries to map that sentence to the space. So that would be great. And I can already say that, it's a spoiler, sorry, but there's no standard of like Word2Vec for sentences. So it's not as mature as work in the space of words. So sentences, we're not there yet. But we tried different things, and other people tried other stuff, and it kind of worked. So we're going to see those things today, and we can discuss about that. The first thing that came to mind was like, okay, I have these vectors, which are, each of them is like 10 in size. What if I just aggregate them somehow? I can sum them, I can do an average, or I can also do a concatenation, which is doable if I don't have lots of words, because if I have a Wikipedia dump, I'm back to the main error. So it kind of works. I mean, the average works, but it's not proven to be semantically perfect. So we have some kind of stuff that you would say, oh, okay, maybe it works, but it really doesn't, and there are not really research papers about it, so we leave it as it is. What the guys, these other guys had published a paper, sorry, I don't remember the names, but what they did was, they did the same reasoning. They said, all right, I have words, and I can average them. Yes, I can do that. But what if I give the network a hint? And what I mean by that is, okay, I'm going to feed my words like I was doing earlier. So I'm going to have the distributed memory and the DBO, which is kind of the CBO and the skipgram. And together with my words, which are going to be averaged here, I'm going to give it a paragraph ID. And what it means is that basically I'm telling the network that that sentence right there is connected to this paragraph ID. I felt it was like kind of cheating in a sense that I'm telling the network that this thing has this class in it. So I'm kind of giving it a hint. But at the end of the day, for my tasks, I can try whatever I want. If at the end of the day I achieve the vectorization of a sentence, great, who cares? So that's what the Doc2Vec did, and GenSim, which is one of the probably most famous libraries in Python for NLP, has an implementation of Doc2Vec. So it's easy if you just go there and try your own. It's gonna work. Personally, I did some experiments and it kind of worked. My problem was that I worked not with articles, I was working more with user queries. So things that people write to buy products. So something like, oh, I want this shirt from whatever brand. So I had things that are like 6, 7 words each. So that's not great. And so this thing didn't work that well. But if we have corpuses like reviews or, I don't know, chats that are between two people in the office, maybe we can try to use this, if that makes sense. Okay, here I'm going to take a big, huge assumption, which is you guys know everything about neural networks, and you guys know everything about CNNs, and you know everything about LSTMs. I have to do this because otherwise we run out of time for sure. And hopefully we're going to have more meetups just about these topics. But here what I would like to do is just to give you the intuition behind what I was trying to do or what I did in my experience to use neural networks to assemble sentences. And the first thing I used was CNN, which is a convolutional neural networks. And convolutional neural networks, whenever you read an article, whenever you Google it, the first thing is going to be something about computer vision, because CNNs were born for computer vision's problem. The idea is that we have a matrix, and every matrix can be represented with a matrix. A picture can be represented with a matrix. And so CNNs were doing some really cool stuff about with the images, and that's great. Those are images. So how does that fit into NLP space? Let's think it through. We have words in our hands that we're trying to stack one above the other. And so what do we have? We have a matrix in a way. So why don't we just try to use a CNN to assemble those words and try to get meaning out of it? The intuition is that the filters that usually are done to detect some edges or things like this in images can give us things like misspellings, which is really common in text data. Or max pooling is going to give us, from a block that we pass to the network, it's going to tell us what's the main topic that we're talking about. What's in that piece of bits that we pass to the network. In a query, it will be the item. So if you Google something like I don't know, newspaper, yellow and blue, we're looking for a newspaper. Now, blue and yellow, it's an adjective, so we don't care that much if it's blue and yellow. The important thing is that it's going to come back with a newspaper. So that's kind of the intuition behind. And then we make it complicated, so we pass to an LSTM, which we hope it's going to keep the word order of the sentence that we just sent. We're going to do exactly the opposite. We're going to flip the network. And the intuition here is that we pass, the first layer we pass, it's an LSTM, it's a long short-term memory network, which is famous because it has some kind of memory. And this is going to help us remember the text that we passed earlier. So we create a sequence. And to give you an example of this, think of when you Google something. Think of when you Google and you say, okay, newspaper, blue and yellow, and then you hit. And you realize that it's not newspaper you're looking for, but it's book. So you come back to scratch newspaper and you write book. That sequence that we're trying to do, that's golden data for whoever analyzes that data. because we're creating some kind of concept which is a session concept, and the LSTM might work there because it's going to track whatever we did one after the other. Yes?
Excuse me, to train this network,
yes.
What was the prediction? What was the loss function
so,
that you used to train the network?
Right, so we're gonna see it because all I'm talking about is gonna be in the demo, so it's gonna be more clear. But to give you an idea, what I was trying to say is that we'll talk in a minute. Just give me one. It's the last slide because I want to introduce the data that I used for the demo, and it's gonna be pretty clear. But essentially, what I was saying earlier is that we have a search, and we have a search, and we have an item. Okay. So we look for newspaper, blue and yellow. My item is going to be a newspaper. So I'm trying to predict that item. How do I do that? If I have an e-commerce, I know that those guys wrote newspaper and then they clicked on buy newspaper. So that's telling me that that's the right prediction. So that's how the network goes. But in general, so I was saying that we create some kind of recurrent network because we're passing data one at a time that have some meaning that relates the sequence that we're passing. So why don't we try the LSTM? The other thing is that the LSTM is gonna, this is something, a parameter in Keras, that it's gonna give us back this thing that you, sorry, there's no thing, but it's gonna give us back what the LSTM produces as an output. So the LSTM is gonna try to take those words that we passed them, it's going to create some kind of the output of the LSTM that you can return and analyze if you do return sequences equal true. So that's from Keras. And we can make some assumptions about these vectors. So this is essentially, sorry if I'm getting too complicated, but this, what it means is that we're pretty much asking the LSTM, okay, I'm going to give you these 10 words. And out of these 10 words, I want you to predict this item. Okay, cool. So how do you compress those 10 words? And here. So what comes out of here, it's what the LSTM does. So we can use those vectors to do some other stuff, but it's interesting to see. And in the end, with the same concept of earlier, we're going to give this thing that the LSTM created to a convolutional network, and we're going to try to, with some filters, analyze it. And we go back to, let's go back to the demo. We're going to see some code. I know that everybody's happy about looking at some practical stuff, otherwise it's just words. It makes sense, it's NLP. Kaggle.com, okay, I took the data from here. I think I can click on it in a second. It was a competition from Kaggle that was done for achieving search relevancy of products. And I'm gonna go to the link in 1 second. And then I took what I was telling you earlier about the global vectors. You can find these things online already pre-trained. So you don't even have to have a computer that eats that data. There's somebody that is doing that for you, and it's putting it on a public repository, so you can just go there, download it, as I did, and use it for your own experiments. And I'm going to go to this page just to show you what this thing looks like. And this is the competition. It was a Home Depot. And Home Depot, it's a store similar to Brico in Italy. And they sell things like hammers and a lot of stuff. And we're going to take a look at the data from the demo. But essentially, it was taken from here. And you can find it. I'm going to share the presentation. And then the link to the global vectors that I was mentioning earlier. You can download them, and they come in different sizes depending on how big you want them to be. Okay, so let's look at some code. And hopefully it's not going to crash. But let's see, first of all, if I can zoom. Too much. Let's do this. Okay, can everybody see the code? Or it's too small? I'll try a little bit more. And like this is going to mess up. So this is the best I can do. If you if you can't see, maybe you want to just approach a little bit the thing. Or I can zoom in, but it's going to squeeze the text and it's going to look, I'm not even sure it looks great. Okay, let's do this. I think the light will make it worse. Yeah, just saying. Okay, so it's not important. So here is where I do all the imports, and I have to compile it. So there's the pressure of the light thing. We make it light to feel the emotion. So this is just a unit function that I'm going to use later. I think I'm not going to use it, but it's kind of give us back some n-grams. And n-grams, what it means, and I think we can discuss this in the really end, but if I have a word, I think I have an example, I'll show you later. So here we load the data that I was telling you about, and it's divided into two data sets. The first one, that it's kind of structured like this. This is the item. It's a Simpson-Strong die go Django, which is something, trust me, I don't even know what that is. But these guys were looking for an angle bracket. And they did angle bracket, and they bought this thing. And somebody manually said that that was really relevant. For now, what we're going to do, this is one piece of the data, which is called train.csv. The other piece of data is this guy, which is called attributes.csv. So in the attributes data, we have all the properties of that product. Okay, so it can be anything from specifying what type of bullet we're looking for, but this thing makes sense. I mean, I thought about a use case to show you whatever I said so far. And trust me on this, but there's a property which is called the tools product type. And what this means is that pretty much is the category of the thing we bought. So and this is an example. So tools product type, we're going to see it later, but we have hand tools, we have power tools, we have tool storage. So it's important that you understand this, the whole picture. So we have somebody that wrote a query, and he said, okay, I want to buy an angle bracket, and then they actually bought this thing. Now this item here, which is a gauge, it belongs to a certain category. Okay. Now what I was saying earlier is that if I can predict the category of this guy, when I search for this angle bracket, then I'm going to pass that category to my search engine, and I'm going to narrow down that search only to those guys that belong to the specific category, hand tool. So I have 1 million products, but in the hand tool, let's say I have 100. So I'm trying to predict this guy, hand tool, so that the search is really hitting 100 items. And those 100 items, they're going to be relevant items, and I'm sure. So if I'm good at predicting this thing right here, I improve search, so from a performance perspective, but the most important thing is that I make the user look at the thing he really searched for. So he's looking at his item, and he's probably going to buy it, hopefully. But whatever is really bad for an e-commerce, whoever works for an e-commerce, is looking for something, and the results that have been displayed, they're nothing like that. Okay, Google is great because we look for something, Google gives us back what we really want, and that's kind of the search made Google what it is today. So that's really important. Now that's the use case. So the only problem of this thing is that that data set is not meant to do that. So if I filter these guys on the ones that have a category, I'm gonna shrink that data set a lot. So I'm gonna end up with a really small data set. So the assumption here is that we're gonna see some accuracies, hopefully. They don't have to make sense 100%. In a sense, don't trust them 100% because we don't have enough data. If you have your own data, if you have a billion stuff, then take this code, and hopefully it's going to work on your laptop too, and do it with big data. Here is just an example to kind of bring everybody on speed and try to make sense out of the things that I said tonight. Okay, so I don't know what I'm doing here. Okay, yes, okay, so this is the example I wanted to show. So we have Husky tool bag, and the category is hand tool. Somebody looked for an impact wrench, and it belongs to power tool. Milwaukee is a brand, stone hole drill, it's a power tool. And what we're also doing is, we need to do it, we need to transform everything. We don't need letters in our AI algorithms, we need numbers. So we map these categories to a number. So with the dictionary or whatever you want to use. There are different ways, and that's one way. So we take the whole list, and we're all interested in the search they made, in the query that they made. And this is just one example. It's impact, driver, drill, battery, power, okay? And that function I was talking about at the very top, called n-grams. What it does is essentially this. So it splits this sentence in n-grams, and I said n-grams of 4, which means I need 4 grams of that word at a time. So it's going to be impact, MPAC, PACT, and you follow this, okay? And the reason why I'm doing this, I'm probably not going to use them here because it's small data, but if you have a big data, going to a more granular way, more granular data, it's going to boost your accuracy. So it's going to make it better. Okay. So now let's do something like this, which is take the whole list of searches and let's calculate the Tf-Idf, that huge matrix that I was telling you about earlier. So, and I don't know if you remember or if you focused on that, but we draw the matrix which is as big as our dictionary. And in our case, our dictionary is kind of poor, but it's 1,200 words about. And we take that matrix and we map for each word. It's not a 1, it's going to be something, I don't show it here, but it's going to be something like a logarithm, because there's a logarithm in the formula, so it's not a 1, but it's 0.36 where the word happens. So we have that matrix now. It's here. It's few lines of code. It's this guy from scikit-learn. And what the vector looks like now is every vector is going to be long 1,200. And we have it for all the queries that we have. Okay, so we have the Tf-Idf. We did that. Now, I did this. Yes, so we split into training and test set. I don't have to comment about that. But we're just going to see that we're talking about 3,000 rows. It's very poor, but it's going to make our reasoning working, so that's all we need. Testing, it's about 20%. So, and here I think it's it's 1 row again. It's full of zeros, and then this is our label. So we have training set, the category which is mapped to a number. So we have query and the number that it belongs to. Great. So this I put it false, but I didn't actually do it. Let's see if I have time, but I don't think I will have time. But this is fastText. So this code, what it does is just puts these guys in a format that fastText accepts. And all fastText needs is to put something like underscore, underscore, label, underscore, underscore, and then the name of the category. And if you put that, then you can just, one line of code enable the fastText. So let's put it false, but I'll go back later. Okay, so we said that we do all of that just to enable machine learning algorithms on top. And I picked 3 of them just because they're kind of the top performance in the classic literature. So I'm going to use an SVM, and naive Bayes, and a random forest. And we can start seeing what the benchmark is. So we're using Tf-Idf, and we're trying to do the prediction. So SVM is 85.48%, and naive Bayes is 82. Random forest takes a little bit more, as you probably already know. And 84.61, pretty good. Actually, this is going to be the best tonight, so that's a spoiler, but probably we're not going to reach 85. So we did that. We did with Tf-Idf. It was pretty simple. It's, I don't know, 50 lines of code. That's great. Now what we do is that I said that we can use Tf-Idf, that is vectors. And they have meaning, they don't have semantic meanings. They have some kind of word frequency in it, but it's not enough. What if we use the semantic vectors? Okay, so that's the link. I downloaded those pre-trained vectors, which are trained on Wikipedia dump, which is 1 billion words. So it's a pretty heavy computational thing to do, but they did it for us, so that's great. I load the vectors, and that's the code that loads the vectors. And I said that king minus man plus woman is equal to queen. But is that really what the network is going to give us? So what I'm asking the model is essentially this. So model Gensim is the model that I loaded. It's the global vector model. And I'm asking what's the most similar, and that's how you do analogies now. Let's not focus on the syntax, but what I'm saying is that my positive vectors are woman and king, and I'm subtracting men. What it's going to be the result. And the other thing I'm asking is, I told you that I can do analogies, but I can also say, okay, I have a vector. What's the closest vector to that? What are my synonyms? And I'm going to input Radiohead, but if you have other suggestions, I'm willing to hear them. So she's back with Queen, which is correct. And I hope there was a Radiohead song, but it's not. And Radiohead, it came back with REM, which is it's actually a band, so it's consistent. And I think you can have some fun with this, trying your own words. And pizza, sandwich, 86% of the probability is 86%, so pretty good. Okay, and you can play with this all day long. Okay, so great, so it works. It kind of works. We can do the analogies maybe later, but this thing works. The only thing that I want you to notice is that if I put something like my last name, it's not in vocabulary, okay? So what I'm trying to say is that you can see the vectors that we trained on it. But if we don't have the word in the dictionary, that's too bad. So we don't have the ways, and we have to retrain the whole network to get that guy in, because we have to calculate, remember, the vector for each word of my dictionary. And that's a tough thing. Some models in Gensim maybe allow you to custom to do it one at a time, but it's a trick, so it doesn't work. Okay. So I was saying we have those vectors, and what we do now is those vectors are 50 in dimension, so a dimension of 50, which is relatively small compared to the 1,000 and 200, which was Tf-Idf. I take those words and I average them. But I take those words from global vectors and I average them, and I'm just building that training set. So what I'm going to have is just one vector of shape 50 that has one vector with shape 50, which is the average of all the vectors that I put into. What I'm printing here is the words that we don't have in the dictionary, again. Now, what I would like you to see is that this, remember we're talking about searches, okay? And what people do, what I do too, it's misspelled search. So here, most likely, it's going to be all the words that are misspelled. For example, hand tools written in just one word instead of two words. Hand tools written with a dash. I don't know, Dramo, I think it's missing an M. And all these words, they don't exist. So this is some kind of interesting data, because from here we can understand what the mistakes are. We can correct them, or we can try to do some stemming, which is something that takes the word and it says, okay, you pretty much say the same thing. If you give me hand tools, or if you give me hand tools, it's pretty much the same thing. So go with it. Okay, so these are all the misspellings. And so I have those average vectors, right? So what I'm going to do is exactly the same thing. I'm going to put those vectors in the 3 models that we saw earlier, and I'm going to see the accuracy of those vectors. Do they make sense? Naive Bayes doesn't take negative values, but that's too bad. I'm going to scale it from 0 to 1. So that's pretty bad. So SVM performs really badly. Naive Bayes, still bad compared to what we saw earlier. Random forest continues to be pretty good. So good job. So the average kind of works with random forests. Okay. So what I'm going to do now is we average them, right? But we said that we were trying to do something like putting all the words and leaving it as they are and just giving it to some kind of neural networks. So we're going to take those words and we're going to create something. We're going to define a maximum length of that query. Let's say that a maximum length has to be 10. Okay, so maximum 10 words of my query. We're still talking about queries, so I don't want it to be that long. We're going to stop at 10. If the thing is short, if the query is shorter, I'm going to add just some padding, which is like zeros. And here we have. So we're still having our data set, which is about 4,000, 10 vectors of PT. So that's what I have. It's a huge 3-dimensional thing. And now let's really try it on Keras. I'm using Keras, and I'm going to try to do whatever I was showing in the slide, which is the LSTM followed by a convolutional network. Not sure we're going to go into all the details here, but I'm going to start training my network. And it's pretty complicated because it has, what I want to highlight is that the LSTM output is 100, and we have about 60,000 parameters, which is pretty intense. And what we want to look here to have a sense of what the network is giving us back, we're going to look at the validation accuracy, okay? Because I didn't split in training and test, but we said that the 20% is our validation, so it's kind of our testing set. So it's growing, the loss is going down, and we achieve 79% of accuracy, which is here. Fair enough. Neural networks, as you probably know, need a lot of data. As I said earlier, if you try this with some more data, we can have a discussion on why that is really low or not. Now we're going to flip the network and do the CNN first, and followed by the LSTM. And same thing, same 20%. It's a little bit bigger in terms of parameters. I'm shooting a big convolution, but 67, starting with 67, we reached the peak at 83.48. So we're kind of reaching our first top performance. Okay, great. We're not very satisfied, so the question is, do we really need global vectors to do all of this? What if we do the same thing, the neural networks, with just some Tf-Idf, so some kind of simple, and sometimes making it simple is better. So what I'm doing is I'm calling back those vectors from Tf-Idf, which is 1,000 matrix, 1,000 in size, and running that matrix in the network. Of course, it's faster because there are smaller vectors, and I think it's a smaller convolution, but we can already see, and this is, sorry, the LSTM. Yes, it's an LSTM, and I'm reaching 83.72. I think this is the best. So pretty good as the other one from global vectors. And then the last thing I'm going to do is try to do the same thing, but CNN and LSTM. Hopefully it's going to be the best of the neural networks. It's slower because there is convolutional networks. And 10 epochs is quite a bit, but. And you can see some statistics about it. This is the LSTM that comes out here. What I was trying to say earlier is that we have the parameter of LSTM that we can put here to say return sequences equal true if we want to analyze those sentences. and that's pretty much it. It's going 73%. We got 83, which is good. 82. It's gonna end like this. And so I'm not expecting to be great. So 84, but this is the best so far. So of the neural networks. So great. This is kind of working. It might work better if we had more data. And remember that the task that we gave to the network is not simple. We're using very short text data. So 10 words, it's nothing compared to an article, to a review that you can find on Google. Those about 200 words, 300 words, where you really see the semantics. Here, we're trying to force the network to do something that is not designed to. But it works. So going back to I'm going to wrap up with this slide. What did we learn, or what the experience says, is that NLP is one of the most mature fields in the AI space. It can give us a lot of value, and there are lots of applications we can think of. Every business that works with text data should consider using NLP to achieve some task. Now, what's the best task? Of course, it depends on the business, but we have very interesting applications today and very easy instruments to download and use, ready to use. Make your own word embedding. We use global vectors. They didn't work that well. Now, the other suggestion I can say is that whatever, for example, you work for a bank and you're using text data from a bank, what I really would suggest you is to try to create your own data set with some context which is related to bank. So you can crawl the web and build some kind of tool that it's not illegal, but that scraps the data and kind of gives the network the semantics of the bank field, because there are things that are in some fields have a meaning, and in other fields can be completely different. I don't have the perfect example now, but there are many. So create your own word embeddings. With a large corpus, as I was saying in the slide, use fastText, at least to have a benchmark of your word embeddings. It's simple, it's very simple. I don't know what time is it, but it's very simple. It's 2 lines of code. And you can easily do it and have your word embeddings. You can benchmark your model and then see if it works. With short text, as we saw, let's go to a character level. I didn't have the time to build all of that, but the thing is, the meaning sometimes is really more granular. And especially in user queries, if you think about what I was saying earlier, is that you can misspell words. You can do a lot of mistakes that trim the word. So what you really care about is the sequence of characters, one after the other. And to not talk about dimensions and all of that, which is a big part of user queries. And the last thing is explore sentence embeddings. Now, what I showed you was my interpretation of my neural networks in a way, my intuition behind them. They work, they don't work. It's really up to your data, to your application, but you can use your fantasy and try. If you have an intuition, go for it, because I think it's worth trying. And if you go around the web, there's people trying all over the stuff, all over the things. Things that probably don't make sense, but I'm pretty sure that the first guy that used neural networks on text data, I'm pretty sure the other people said, "Oh, are you crazy?" It's always like this. I mean, it's always something that it might not be that intuitive, but it could work. So keep experimenting whatever you have in text mining. So I take questions now.
What do you intend for a large corpus in the case of fast?
So large corpus. If we talk about queries, it's a big number of queries, right?
How many?
How many? Personally, I worked with 5 million queries a day. So that's kind of a lot. maybe I would say a fifth of that would be enough. So a million queries can give you some insight. And I just wanted to add that the session, the concept of having the query after the other, so when people type and mistype and they write again, they scratch and they rewrite again, that's really important. That's something that Google does, and it's kind of following you. I don't know if you noticed, but if you type some stuff, then the next search is going to be related to the first one. Now, I'm not sure what type of LSTM they have, but I'm pretty sure they have an RNN running in the backend.
In the past, I'm talking about mostly about the translation. There was an approach that was not based on neural network and stuff, but more on grammar, you know. And there has been a lot of work on this, and there were commercial products actually pretty expensive about it. Is this line completely disappear from the scape with this kind of, with this analysis, which at the end is statistics?
Yeah. The answer, I don't think it's not no, in the sense that parsing, this is more like parsing the query. It's very important. Like, there's going to be something that you do automatically, but there's always going to be that piece that it's right there waiting for you to be parsed manually. So you need a person to go there and build a parser for that specific queries. Maybe the queries that belong to a specific field that is 2% of your products, but we need the parser. So we're not going to abandon all the works that have been done. I mean, for example, regex, it's like the basic of NLP is like you first try to parse and then maybe you classify things. But regex won't disappear. It's like for sure.
Okay. The other thing is, if you are saying so, it means that you know, apart from treating generic questions, you know, to larger corpus like the thing that you and so on, there is plenty of local entries, you know, like in translation, for example, mechanics, you have this controller language and stuff.
Yeah.
In that case, probably you will have a super hit because you have a constrained vocabulary and your similarity will go higher.
Yes. Yes, I mean, one thing to add to what you said is that word2vec, one application of word2vec is they showed that you map your data with your language. Let's say it's Italian. And then you map the language in English.
Yeah.
The mapping remains. The semantic is the same. So with the matrix rotation, you can do translation, which is pretty impressive. Yeah. And like, it doesn't know anything about the languages, but you can map it. And those semantic vectors will stay, will hold the direction. So that was impressive when I saw it. But that's one of the applications.
Yeah.
Yeah, you said that fastText is very fast with respect to word2vec and knowledge embeddings. So, what's the what reason not to use the fastText?
It's hard to say. No, in the sense, that's why I was saying use fastText. It's very fast. It allows you to do with one command. So the command will look like this. I'm going to zoom.
Hey.
Sorry.
Oh, wow.
Hold it.
Okay.
Okay. So here, what I'm calling is fastText, which you downloaded. I'm actually testing here, but okay. So input, I'm passing the input. I'm saying, okay, pass me the output. And what I can specify is 10 parameters where you can already do the n-grams, just putting a flag that says dash n-grams. That simplifies a lot of work. Like the function that you saw that n-grammed in Python, it's still code to write. Here, everything comes in the package. So it's really hard to abandon fastText. I think if you want to combine fastText, it's like what I was saying earlier. You're gonna need to do some customized stuff that fastText will not allow you to do. Okay? So if you call fastText, I think there is a Python library version of it. I'm not sure. But if you use that together with Python and together with some customized things you can do with those words, then it makes sense to always use fastText. Otherwise, if you find limits to do whatever you want to do with your words, then you will have to put fastText on a side, and that's going to be your benchmark, because it always gives you very good accuracy. And but you can't. What if you want to do deep neural nets? Deep neural nets, in my experience, beated the fastText. So it was a really deep neural net, but it beat fastText. Now it was way slower, but it's better. So are you looking for performances or accuracy? Now that's your trade-off. But that's one reason neural nets can be better than fastText.
I have two questions. The first one is about sentences, working at the sentences level, because how can you handle an incremental corpus with new sentence that you've never seen before opening? How can you work with an embedding of sentences when new sentence arrives?
And that's kind of the problem, also for word-to-vec, in the sense that every time you have a new word, you will have to retrain your network.
Okay.
GenSim gives you some chances to not do that every time, but it's a trick. So if you really want to do it, you will have to retrain it. Now it's a backward, but you know we have to do
So
some
otherwise
trade-offs.
use the infamous unknown, but you can, of course, I expect, unless you have a very, very large corpus at the beginning, the probability of having a total new sentence is quite high, right? So it's better to use it when you have a large corpus.
Exactly. I mean, with large corpuses, it will definitely work better. A small thing, it's tough. I mean, it's like forcing a little bit the job, but it gives some results.
Okay. And the second one is something, maybe to me, I've never seen it before, is the use of n-grams. So basically, you just cut the words at a certain amount of characters.
Yeah, and that's, in my experience, in those short texts, they help. It's always better than the entire word. And what I was saying earlier about the misspelling, about the stemming, it comes for free if you do the n-gram, because you will know the word but you also know the word misspelled as war without the D. So it's going to take that thing and say, okay, that's my most important piece of the sentence, of the query, so it works.
Do you slide the
Yes,
window?
it's a sliding window. Yes.
Okay. So
yes, I'm sorry, I didn't specify, but there was sliding the whole sentence. So it slides and you have 4 at a time or 3 at a time.
And you don't do an embedding, but you put it inside a...
You can embed it. It's up to you. You have 2 choices. You can either embed it in those guys or put the entire word in it.
It's very interesting. I've never seen it, but very interesting.
Yeah, no, it's definitely going to help your network. I'm almost sure. And now it's going even to a more granular way where you have only like single letters and bigrams. It's interesting. Yes.
Can we find an embedding data set for Italian language, just like the Globe?
I think there is a website that has the repository of all the train vectors. I'm not sure it's trained with word-to-vec or glove, but it will work anyway. And they kind of post for each language and for each field, they post this data set. If I find that website, I'm gonna send it to you right after, or post it on the website. But there is a kind of a public repository where you find all the data sets, which all the pre-trained vectors, which is it's some kind of good job that they did for the community.
Yeah, like that. I don't know if you have used Spacey. It's a library which contains a lot of pre-trained language models.
They come for free in the library.
Yeah, so if you use Spacey, you can load a lot of already trained language models. And I have a question.
Yeah.
So you gave a very exhaustive overview of all the techniques. Really good. I'm wondering if you also had a chance to experiment with sec2ec or any other deep architecture using attention models.
If I did in my past, or
if you compare with.
I don't have experiences with those very deep networks. What we did was using the standard tools, pass me the word, but like Word2Vec or Doc2Vec or until the fastText came. After that, we said, all right, let's do it ourselves. So if we can do it, we can do it maybe better. If you know how to use neural networks, I think there is value in it. In fact, the first network we tried was better than fastText, so there was no reason for us to go to another prepackaged thing, but I'm not sure how good it is. Yes?
If you use Word2Vec on n-grams, you don't have the risk to lose the semantics of n-grams compared to Word.
I think so. I never done it. I still think that there is you're gonna map some things they would make sense and some others they won't. It's also a matter of how you choose the context that you're moving your Word2Vec in. So if you choose a really short context, so you train your trigrams in 10 characters window, maybe there is good results. It's a good observation. I'm gonna try it, but I didn't try it myself, so that's just my view. Okay. Thank you, everyone, for. I think I can share the code with everyone, right? We can post it.
Yeah, it's on GitHub or?
I can put it on GitHub.
Yeah.
Well, of course. If you give me a free account.
There is
No, the preview one. There is a preview
one. We can request one.
Okay.
But yeah, we will share.
So I'll try to share the code and the slides.
Yes. So before we end the event, I forgot to say that we have another meetup. It's going to be on July the 11th, and it's going to be in Surf, and it's in San Donato, right? Same office, right? Like last one, and it's going to be about Kaggle competitions. So stay tuned. Thank you very much.